Assalamu alaikum everyone, good evening, and welcome to the sixth and final session of DevFest24 Talks. My name is Taibi Mariam, and I will be the animator of this session, in which we will be introduced to the fascinating world of reinforcement learning by Mr. Nazim Bendib, who is a master's student at Sorbonne University, an alumni of EASY, a machine learning research intern at NYC University, Abu Dhabi, and an NVIDIA Deep Learning instructor and ambassador, among other impressive accomplishments. Mr. Nazim, welcome and thank you for joining us today.
All right. Hello, everyone. Thank you so much for the introduction. So happy to be here with you for the fest. Pretty exciting talks. I'm glad that it's the finishing talk. So yeah, it's an honor, actually. Thank you. All right, so should we start now?
Yes, with no further ado, Mr. Nazim, please, you may start.
All right, thank you. Okay. So yeah, tonight's talk is about an introduction to reinforcement learning. I will try to explain like the basics of the basics without going into too much mathematics and background behind it. I will try to keep things pretty light. I will try not to talk like purely in English for the whole session. And yeah, I'm happy to answer all of your questions by the end of the talk. So, okay, about me, my name is Nazim Bendib. I'm an alumni from the Higher National School of Computer Science, EASY. I graduated this year, and now I'm a master's student at Sorbonne University doing artificial intelligence. So, yeah. And I'm also an NVIDIA Deep Learning instructor. So, yeah, from time to time, I deliver NVIDIA workshops, mainly in fundamentals of deep learning and about transformers in NLP applications. So yeah, without further ado, let's start. A bit of the introduction. So what is reinforcement learning? Of course, it's a subfield of machine learning, which is itself a subfield of artificial intelligence. And it's pretty cool because in reinforcement learning, we don't just simply have like data and a model and we train and we do regression or classification. It's much cooler than this. So in the general context of reinforcement learning, we have an environment which can be a game or a maze or whatever it is, and we have an agent in there. So the agent can be a robot, an animal, anything that can act on the environment. So the agent is going to select actions or make decisions and apply these actions on the environment. And the environment is going to get affected by those actions and return some sort of a feedback signal to the agent. So we call this feedback signal a reward. And yeah, this reward is going to tell the agent whether its action was good or bad. So generally, this reward signal is going to be a scalar. Generally, it's positive when it's a good action and it's negative when it's a bad action. But the goal isn't like simply positive, negative, but rather the agent is going to try to maximize the reward. So تقدر زعما الريورد دايما تكون positive and the agency maximizeها. The higher the reward, the better it is. And the goal of the agent is not simply to maximize like the immediate reward that he's getting, but instead it tries to maximize the cumulative reward over time. تما ما يشوفش برك غير تماك rather راح يشوف شغل في الفيوتشر ويساي maximize the cumulative reward over the whole session. So as we can see here, let me just activate the laser. Okay, so yeah, we have the agent and the environment, the two main components. The agent is going to select an action A. So during the whole session, the actions are going to be A. And the environment is going to return a reward, which is denoted by R, and it's going to return a state, which is denoted by S. And so the reward is, we're going to use it in order to update the agent, which can be a simple table to a highly complex neural network. And we're just going to update it using the reward. And the state is just going to be the input to the agent. Parce que le rôle d'un agent who to take a state as input and output an action. And we have this loop. So the agent selects an action, the environment gets affected, return a reward and state. The reward updates the agent, the state goes as input again, and then the agent selects another action. اغبرت حتى الايجنت يتعلم ولا ما يتعلمش ولا المهم نكون غادي نديرها له. So Super Mario can be considered as a reinforcement learning problem. So the environment here is the whole game with the turtles, with the blue tunnels, with all these question marks, etc. This is all the environment. And the agent, of course, is Super Mario in here. So Super Mario needs to learn that it should avoid like hitting turtles, avoid going into the tunnels, etc. And the goal is, of course, to finish the game without doing any of these bad things. So in here, we can, for example, create a reward function that says, if you touch a turtle, then I'm going to give you -10. So it's a penalty. And Super Mario in the next games is going to learn that touching turtles gives me a penalty. So better avoid touching turtles. And so راح يتعلم avoid the turtles and so on. So لو كان يدخل داخل التانل and يخسر لابارتي كيف نعطوا a penalty. إذا ياكل هاد المشرومز هادو يكبر, maybe we can give it a reward to tell Mario that, yeah, it's good to eat mushrooms because you're more likely to survive the game, and so on. So the reward function احنا نخدموها كيما رانا حابين. بصح لازم نخدموها in a smart way in order to guide the agent towards the main goal. And yeah, so pretty much we define everything. The environment is the game, the agent is Super Mario, the reward we can set it up كيما نحبو, and the final goal is to finish the game. So إذا زعما Super Mario كمل الجيم كامل والحق الفلاج هذاك نعطولو a big reward. Par exemple, +100. باش يفهم بلي yes, finishing the game is important and I need to finish it next time. So better avoid all these obstacles. All right, so this is just an example of a reinforcement learning problem. Now, in reinforcement learning, we have like some main components. So mainly we have the agent, who was the actor in the environment. We have the environment, which is like the whole simulation, the whole system. We have the action, which is like the set of decisions that the agent can take. Par exemple, في الكات تاع Super Mario, actions هنايا راح يكونوا moving forward, moving backwards, jump. I don't know if he can dock or not. مانيش شايفين. بصح mainly these things. شغل actions اللي يقدر يديرهم بسوبر ماريو. سي هو يبوجي يصوتي etc. Okay. The reward كما قلنا, it's a feedback signal returned by the environment to tell the agent whether the action is good or not. We have the state, which is the current state of the environment. For example, the frame itself is one state. If I go to like another frame, it can be considered as another state. And so each time the agent performs an action, it's going to move him to another state. So we call these state transitions, and we're going to see them more in detail later on. So yeah, we call them states, and we have the policy. So the policy is the strategy that the agent is going to learn. Basically, the policy tells the agent which action to take at a certain state. البوليسي هي الخطة تاع الايجنت, سي لا استراتيجي تاعو. تما الايجنت راح يجي ستيت, using that policy راح يعرف شنو الاكشن يخيرها. انا راح نزيد نشوفوها later on. All right, so now let's talk a little bit about state and actions. Here I have like a smaller environment, I would say a simpler environment. So this is a maze. الميز فيها الديكارو وفيها الوولز هادو اللي لازم نتمشيهمش. Of course راح نبدا من top left والgoal is to go to the bottom right باش نلحق الفلاج هذا. So الايجنت تاعي سي هذا البوان جون هذا وراح نقدر نخبط ونطلع اتسيتيرا حتى نلحق الفلاج. So each one of these is considered a state, like a different state. So for example هنايا كنا هنايا, the agent is going to take an action. For example, he's going to go down, and so he moves down, and this is considered another state, and so on. So he decides to move right, another state, and then we move right again, we go to another state, etc. So we call these state transitions because we are transitioning from one state to another. En grosso modo, a state represents the current situation or configuration of the environment, and the action is a decision made by the agent that affects the state of the environment, leading to transitions between states. Je pense que هنايا c'est clair. A state is the current situation, and an action is the decision that the agent takes and affects the current states. Okay, now again, the reward is a feedback signal indicating how good or bad an action is, guiding the agent to maximizing long-term gains. So for example, let's consider this first scenario. We have the agent here in state I. So he decides to go up. Well, the agent, I'm going to say he, not it. He decides to go up, state I plus 1, and then let's say he tries to go right. If he goes right, he's going to hit the wall. And it's not really a good decision because you're not supposed to hit the wall. So yeah, I'm going to give it a penalty. So reward equal -1, saying that the penalty is negative. In the second scenario, let's say we were like 2 steps before the final reward, and then we go down, and then we go down again, and we reach the flag, and cool. We reach the goal, and we get a reward of 10. Telling the agent that, yeah, that was like a perfect scenario. I encourage that. So next time, try to do the same. Try to come here and then go down and down until you reach the final state. We call it the terminal state. So yes, after each action, we are going to give a reward or a penalty to the agent. So now the environment is going to look more like this. At each step Si, the agent is going to select an action Ai that moves it to another state, Si plus 1. And at the same time, it's going to give it a reward Ri plus 1. So each reward is assigned to a corresponding state, okay? And we keep doing this. So now instead of having these visuals in here, generally we represent an environment as an MDP or a Markov decision process. So we have the states, we have the actions that make the transition between one state to another, and at each state we can get a reward. So Si, we select action Ai, we go to state Si plus 1, and we get a reward Ri plus 1. And then we do the same. We select another action, which is going to be Ai plus 1. We move to state Si plus 2, and we get a reward Ri plus 2. And we keep doing this. So here we defined the actions, states, and the rewards. And these are the main components of every reinforcement learning algorithm. We are going to use them everywhere. Okay, now let's talk about the policy. As I said before, the policy is the strategy that the agent follows. And in simpler terms, we can consider it as a function that maps the space of all states into the space of all actions. So we refer to it as P. So P goes from S to A, and it's like a mapping, literally. So we have all the states, we need to map them into an action. In even simpler terms, it's a function بنمدوا لها a state as input وراح تريتورن لنا an action. As simple as this. Now this policy can be represented by a simple table like here, or it can be represented as an approximation like using approximators, and it can even be represented as a whole neural network, which is a huge approximator. We can use CNNs, graph neural networks, etc. So anything you can manage to do. So yeah, here I try to create a small policy table. So we have 2 columns. We have a state column and an action column. And as you can see here, for each state, I assigned an action. So for example, the state here represents the coordinates of the position of the agent. So let's say if you were in the position 0, 0, which means we were here, then the action was to go down. So we go down. And then we are in state 1, 0, which is this scene here. So the action says go down again, so we go down again, and we keep following this policy. All right? So the ultimate goal of reinforcement learning problem is to actually learn the good policy, because at the beginning, you have like a random policy. You don't know which action to take at which state, so it's random. But then after the training, you ideally converge into a pretty good policy, or even better, an optimal policy that maximizes the cumulative reward by the end. So, okay, that is for the policy. Yeah, so that's the big question, actually. How are we going to do to learn a good policy? اوكي انا حاط الكاس في القاعه، ما نحطوش قدام البيسي باسكو نخاف نقلبو. تسمى مانياك شويه. Alright, how to learn a policy. Yeah, so I mentioned this before, but I think it's better to mention it again. The goal in reinforcement learning problem is not just to maximize the immediate reward. ما نشوفوش à court terme, نشوفو à long terme. The goal is to maximize the cumulative reward. So the cumulative reward, which is denoted by G, is basically a discounted sum of all the rewards that we are going to get. So for example, let's say we are in state Si. So if I want to calculate the cumulative reward in here, it's going to be Ri plus 1 plus Ri plus 2 plus Ri plus 3 plus Ri plus 4, etc. until like the end of the end of the episode. And so, yeah, generally we don't just sum them up, but rather we add a discount factor just to make sure that it does not diverge. So it's like theoretically proven to converge, right? Even if like the episode is infinite, like we don't have a terminal state. So these are just details, but what you need to keep in mind is that the goal is to maximize the cumulative reward, which is GT, which is like summing up the rewards that are going to come, instead of just simply maximize the immediate reward. Because that's the thing. Generally, environments are complex. And sometimes if you take like the best action immediately, it's not going to lead to you winning the game. So for example, if you take chess, getting the queen can be considered as like an immediate reward. But it does not mean that you won the game, because like it can be like a smart sacrifice and then you're gonna lose the whole thing later on. So we need to be smart in our decision making. We don't just jump on to the immediate reward, but rather we need to think about what's coming next in the next steps. So yeah, this is the cumulative reward. And now we need to define something called the state value, which we are going to use a lot later on. So a state value is an estimation of the cumulative reward that we can get from a certain state. حنا كيكونوا في ان environment جديد ما نعرفوش، نكونوا in a certain state ما نعرفوش really the cumulative reward that we can get because it's an unknown environment. We didn't explore all of it, but rather we can have an estimation, okay, based on the policy that we are following. So it's an estimation or an expectation following policy P of the cumulative reward. So this formula in here, maybe I can do this. Yeah, so this one in here is no more than the cumulative reward. This one, okay? So it's an expectation over the reward that we can get, given that we are in state S. And كيفاش نقدروا نشوفوها؟ It's simply an estimation. رانا in state S، نحاولوا نعرفوا هاد state شحال راهي مليحة ولا مش مليحة. Maybe كان لازم ندير لكم chess examples in here, but like given a board of chess, نقدر نستعمل my position. اسكو راني بيان ولا مانيش بيان. It's exactly the same thing. But yeah, this is the state value. Now let's start with a very famous set of algorithms called dynamic programming. And it's widely used, especially back then, it's widely used in reinforcement learning, like in solving reinforcement learning environments. So dynamic programming is a collection of algorithms that can be used to compute optimal policies given the perfect model of the environment as an MDP, as a Markov decision process. So we don't actually use dynamic programming for all environments, but rather we use them for environments on which we have like the dynamics of that, like the model of that environment. In simpler terms, كي نجيبوا un environnement surtout إذا كان complex مش هنعرفوا like states اللي راح نروحوا لهم from a given state because we're just exploring, right? And so we can't use dynamic programming. So for dynamic programming, we are going to assume that we know the transition probability, which is like the probability of going to state S prime, given that we were in state S and we selected action A. So let's say we are in state S, like in here, okay? And then we decided to select action A. So for example, we decided to select action 2. Now, selecting action 2 does not mean that I'm going straight to S prime, because I can have multiple S primes to go to. I can have like different or multiple states to go to. And each state has a probability equal to this, okay? So for example, if this is S prime 1, S prime 2, S prime 3, then I need to have like probability of PS S prime 1, given that I was in S and I selected action A. And this probability, I don't always have it, especially in like complex environments. So if I have like simple environment and I have access to these probabilities, then I can of course use dynamic programming, and it's guaranteed to have an optimal policy by the end. Okay, so one last time, this probability means that it stands for the probability of selecting or of going to state S prime, given that I was in state S and I selected action A. Now, there is a very famous algorithm or method called policy evaluation, which is a formula that allows us to create a value function, which is like V, given a certain policy. So عندنا policy, عندنا strategy, ونحوسوا بهذيك البوليسي نيفاليويو الستيت تاعنا. Then we use this policy evaluation formula. So this may look complex, it may take a bit of time, but we need to understand this. Okay, let's say I want to calculate or to estimate the value of state S, which means that I want to evaluate this state in here. It's going to be the sum of all actions, all right? So A is the actions. So for example, it's going to be the sum over action 1, action 2, and action 3. And then for each action, I'm going to take the probability of selecting that action, given that I was in that state, given that I'm following a policy P. So هذه وش معناتها؟ كما قلنا قبيلة, P is the policy, and P given S means what is the probability of selecting action A إذا كنت في state S. All right, and it's returned by the policy that I learned. So I take this probability and then I further multiply it by this term in here. So in this term, I have a sum over all future states, S prime. Because if I am in state S, and for example, I select action A, then I have, for example, 3 future states, okay? So again, I use the transition probability, which is the probability of going to state S prime, given that I was in state S, and given that I selected action A, which in this case is action 1. And then what I do is that I take the reward that I get of going to state S prime, given that I was in state S and selected action A, plus the evaluation or the value of that particular state, okay? And we call this propagation because we are going to calculate the value of state S based on all of the values of the possible future states, okay? So we are going to sum over all actions, and for each action, we are going to sum over all its future states. And by doing this, we are going to propagate the values of all future states into the value of the current states. And we keep doing this iteratively until we have like a value function that converges. And it's going to like accurately return a value for each state given this policy. Now, something to note is that we are not going to learn a policy from here. We are just going to evaluate states given a certain policy, okay? And I highlighted this, given a certain policy. All right. Now we have another algorithm, which is called policy improvement. Now we have the value of each state, and we want to create a newer policy or an even better policy. Okay? So كما قلنا قبيلة, a policy is just a strategy that we want to follow. So policy improvement is the process of updating a current policy P to a new policy P prime that maximizes expected rewards based on the value of states V under the current policy. So let's say I want to update the policy in state S. Again, we are in state S. Okay. So it's going to be the argmax now over the value of future states. So let's try to understand this. It's very similar to the previous formulation. Here we have the transition probability of going to state S prime, given that we are in state S and we select action A, multiplied by the reward that we can get, plus the value of state S prime. And we are going to do this for each action. So we are going to calculate this in here, we are going to take this, and we are going to take this, of course, for each action. And then we are going to select the action which has the max or the highest value of future states. And that action is going to be the best action for state S. كيفاش نقدروا نشوفوها؟ نحكموا state S، نحكموا كامل possible actions that we can take, and then for each action نشوف estimation تاع the cumulative reward في future states تاعها. And bien sûr ماذا بيا ندير action اللي تماكسيميزي لي future reward. So we take the argmax. Argmax is, for beginners, it means that it's the argument of the maximum value. Okay, we're not taking the max value, but rather we are going to take the action with the maximum value. So for example, action 1. All right, so next time when we are in state S, we are going to select action 1. parce qu'à حسب la formulation هذه عرفنا بلي action 1 راح تريتورني لي the maximum expected value. All right, and now using both policy evaluation, which evaluates a certain policy and creates a value function, and using the policy improvement, which is going to create a new policy given that we have a value function, we are going to create a new algorithm called policy iteration. So using policy iteration, راح ندوزو على plusieurs itérations, where at each time واش راح نديرو راح نحكموا البوليسي تاعنا نديروا لها evaluation تسمى نجيبوا ال V, and then in the next step نحكموا ال V هذيك ونخدموا بها a newer policy, and we keep doing this iteratively until we have a convergence. So we start with a random policy P and a random value, and we keep doing this iteratively. So تكون عندي policy P نخدم بها value V, and then that value is going to update the policy, and then the policy itself is going to create a new value function, etc. And we call this improvement. Now, by the end, we are going to end up with an optimal policy. اللي راح قد ما راح نسيي نبدلها مش راح تتبدل because it's the most optimal one. So we call this a convergence. كيما لقيناها en maths point fixe. It's very similar to that. And so the optimal policy, which is denoted by P star, is the policy that is going to maximize the cumulative reward. And the optimal value is the value function that is associated to that optimal policy. So this was policy iteration. Now we have another family of algorithms called temporal differences. So in here, we don't have the dynamics of the environment. We don't per se have the probability of transition. I don't have the probability of going to state S prime, given that I am in state S and I selected action A. So I can't use these algorithms because this term in here is missing. I don't have it. And it's the case in most of the environments, right? نقدر نخدموا بهاد لي algorithms تاع policy improvement غير كي حنا نخدموا الام دي بي هذاك ونكونوا شغل نكونتروليوه بيان. تسمى تكون عندنا لا فالور تاع لا probability هذه. Par contre, in most environments we don't have access to that, so we need to come up with smarter ideas. So yeah, let's build an intuition behind it. Let's say I have state ST, I select action AT, and then I go to state ST plus 1. All right, so by going to st plus 1, I gain a new reward, which is rt plus 1. Now, ideally, like in best case, vs of t, or the value of st, is going to be equal to rt plus 1 plus the value of st plus 1. All right, so كيفاش نقدروا نشوفوها؟ الفاليو تاع st plus 1 is the estimation of cumulative rewards اللي راح نجيبوهم if we start from st plus 1. So basically it's an estimation of this, of everything that comes in here. Okay, when I راني نحب نحسب the value of st, which is an estimation of the cumulative reward, if I start from st, which is basically this. Okay, so it should be the reward between st and st plus 1, which is this bit in here, plus the value of st plus 1, which is this one. Okay, so it's a mess in here, but I think you got the idea. So ideally we have this. Of course, we multiply by discount factor, but let's just ignore it for now. The problem is that I don't always have that, because this is ideal. So there is generally an error, like a small difference between them. We call this an approximation error, or we can even call it a temporal difference error. We denote it by sigma, by delta. So delta t is equal to rt plus 1 plus the value of st plus 1, which is this term, minus the value of st. Okay? And this is going to be the difference. So it's the difference between the current evaluation and the future evaluation. And so we are going to use this to further update the value of st. Okay? It's like gradient descent in neural networks and machine learning. So we are going to update the value of st by the value of st plus alpha, which is the learning rate, multiplied by this difference in here. Now, if this difference is positive, then it means that this bit in here is going to be superior than this one, which means that we need to increase the value of st. And so the value of st, like the new value of st, is going to be the old value of st plus a positive term, which is going to push it like a bit higher, and vice versa. If that delta is lower than 1, then it means that VST is overestimated, which means that we need to decrease a bit of the value. And it's going to happen automatically because VST is going to be VST plus a negative term, which is VST minus a positive term, which means that we are going to decrease the value. So this is the update function in temporal differences. At each time step, if we want to update the value, it's going to be the current value plus alpha, a learning rate, multiplied by this temporal difference, which is the reward that we can get, plus the future evaluation minus the current evaluation. And we are going to use this in all of the temporal difference algorithms. So this in here is a small pseudo algorithm of TD prediction or temporal difference prediction. So this is the formula again that I showed you earlier on. We have P, the policy, to be evaluated, okay? And yeah, we have like a random value in the beginning. So we start with something random and we try to converge. Now at each step of the episode, we are going to select an action A, given that we are in state S, and we are going to observe a reward R and the future state S prime. So now we need to update the value of S, like the current state. It's going to be equal to the current state plus alpha multiplied by R, which is the observed reward, plus the value of the future state minus the value of the current state, which aligns perfectly with this formula in here. And then we move on to the next state and we keep doing this. So at each time state that we make, we are going to update that state and we move on. And by doing this iteratively, we are likely to converge like into a good value by the end. But again, we're not learning any policy in here because we're simply like updating the value. All right, now before going any further, we need to define another function. It's called the state action value. So later on, we are assigning a value to each state, which is an estimation of the cumulative reward that we can get, given that we are in that state. Now, we are going to do something very similar. Instead of estimating the whole state, we are going to estimate couples of state actions. So we are going to assign an estimation to an action A, given that we are in state S. كيفاش نقدروا نشوفوها؟ نقدروا نشوفوها نقولوا بلي احنا عندنا في state S وخيرنا action A. It's an estimation of how good was that action from that state. Okay? So كيما تشوفوا هنايا la formule c'est exactement la même, but the conditions يتبدلوا. So we are going to evaluate all of the tuple instead of the state only. All right, and so we come up with another algorithm called SARSA, which is like a fundamental one. So now at each time step, we are going to be in the current state, which is S. We take action A and we observe the reward and the future state. And then from that future state, we also select another action, which is going to be called A prime. So in S prime, we select A prime. And so we are going to update the state action value using this formula in here, which is very, very similar to the old one. Because now instead of updating the value of states, we are going to be updating the value of state actions. And it's going to be the same. It's going to be the value of that state action plus alpha multiplied by the reward that we observed, plus the state action value of S prime A prime minus the state action value of SA. And we keep doing that until convergence. So this algorithm is called SARSA. We also have another algorithm, which is called Q-learning, which is very similar to SARSA, but it's a bit simpler. Because in SARSA, in order to make an update, we need to also select another action for the future state. So non seulement رانا in state وخيرنا فيها رانا في state S وخيرنا action A ورحنا للstate S prime، لازم تاني نكون عارف وشنو هي الاكشن هنخيرها في S prime, which is A prime, in order to make the updates. بس in Q-learning it's simpler. Il suffit برك نكون في state S نخير action A, I go to state S prime, and then I assume that I'm going to select the best action in S prime. تسمى ما نتسناش نتبع الالغوريزم ونشوف واش هي الاكشن اللي حنخيرها في S prime. But rather directement ناسومي باللي in S prime I'm going to select the best action. And that's why we have the max in here. We are going to be selecting the best action. So this is Q-learning, which is like, I think it's more famous than SARSA. أنا وبزاف عباد اللي يقراو في اسمه learning دايما كنا نسمع Q-learning before going into SARSA. And so the Q-learning algorithm is going to be as follow. So at each step of the episode, we are in state S, we select action A, and then we observe a reward R, and we go to state S prime, and then we are going to update the state action value. So it's alpha multiplied by the reward observed plus the maximum minus the state action value of the current state with the current action. And we keep doing that. And كما راكم تشوفوا, in both SARSA and Q-learning, we don't have the probability of transition اللي كما كنا نشوفوها في dynamic programming algorithms. هنايا نقدروا نجيب an environment ما نعرفوا عليه والو, and just by exploration we can learn a good estimation of the values تاع states ولا تاع state action values. And by doing so نقدروا نخدموا البوليسي تاعنا using something very similar to to the policy improvement. نحكموا الفاليو تاعنا and نخدموا بها a policy. What we can do now is that since we have the state action values, وشنو نديروا نقولوا زعما كي رانا في state S نروح نشوفوا الاكشنز اللي نقدروا نخيروهم في state S, and we simply select the action with the maximum value تاع state action value. Okay? And this is what we do in both SARSA and Q-learning. Sometimes we can use something called epsilon greedy to not fully exploit the policy and to encourage exploration. Sometimes in the policy we select the best action given like the Q value, or we can select a random action باش نروح نexplore like newer states. All right. So yeah, in conclusion, we've seen, we talked about reinforcement learning, like a brief introduction. We talked about the main components of reinforcement learning. We defined what is a state value, which is an estimation of the cumulative reward, given that I am in state S. And we defined the state action value, which is an estimation of the state action of the cumulative reward that we can get from being in state S and selecting action A. And then we've seen two sets of algorithms. We've seen the dynamic programming algorithms, in which we had policy evaluation, where we evaluate a policy and create a value function. And we had the policy improvement algorithm, where given a value function, we create a newer policy. And then we've seen a combination of both in policy iteration, where at one time I do policy evaluation to evaluate the policy, and in the next time I do a policy improvement step, where I try to improve the policy using the previous estimation. And we keep doing this until convergence. And then we've seen the temporal differences algorithms. We've seen like the foundation of it. We talked about SARSA and we talked about Q-learning. We highlighted like the main differences between them. And this is just the beginning, I guess. These are like very simple algorithms, and generally here we only use, we call them tabular algorithms because we don't need approximations. But when we try to scale up to like bigger problems, we need estimators, because like we've seen here, we can't always have a table like this. Generally, if we have like a huge number of states and a huge number of actions, then it's going to be pretty impractical. So what we try to do is to use an approximation, ideally using like a neural network, where we pass like a state as input, and we are going to predict the action as output. And we call these approximative methods. So still in these approximative methods, we still use Q-learning, but we give it like a fancier name. It's going to be called deep Q-learning because we use deep Q-nets. And then from Q-learning, we have double Q-learning, double DQ and double deep Q-learning, etc. And then we have like other families like optimization-based ones, etc. So yeah, thank you for attending. If you have any questions, I'm glad to answer them.
Okay, I've been checking for questions. Apparently, we have no questions. So I'm gonna just move to the conclusion. Well, now we have arrived to the end of today's session. I would like to extend my thanks to Mr. Nazim Bendib for his insightful presentation. And of course, a big thank you to you, our wonderful audience, for your engagement and attendance. With that, ladies and gentlemen, we've officially concluded the DevFest24 talks. I want to express my gratitude to everyone who helped make this season's DevFest a success, especially our outstanding presenters and our supportive audience. But remember, while the talks may have come to an end, DevFest24 is just getting started. We still have more surprises in our pocket, so stay tuned and make sure to follow us on our social media to keep up with what's coming next. And GDG for once, GDG forever.